Forget about exploring distant stars for a minute. Today, we're going to journey into a universe that's just as complex, way more vital, and, well, it's right underneath your feet. We are talking about soil, so let's dig in.
So, when you think about the ground, what really comes to mind? Is it just dirt? Something you wash off your boots and don't think twice about? Well, get ready, because we're about to completely change how you see it.
Just take a look at this. Now, it might look like a piece of modern art, and it's beautiful, right? But what you're actually seeing is a microscopic slice of soil. This is where our journey begins, uncovering this incredible, ordered universe that exists in every single handful of Earth.
We're going to start by zooming all the way out. We're looking at the entire planet. Because just like we have climate zones or oceans, soil has its own global geography. This map shows the world's major soil regions, what scientists call orders. And these aren't just random splotches of color. They're drawn by climate. See all that blue up north? Those are frozen soils called gelisols. And the pink running along the equator? Those are ancient, super-weathered oxysols. The whole planet is like a tapestry woven together by temperature and rain.
But okay, this isn't just a geography lesson. This global map, it actually holds a really critical clue to one of the biggest challenges we're all facing, climate change.
Let's focus back on those blue gelisols up in the Arctic. You can think of these permafrost soils as a giant carbon freezer. They've stored massive amounts of organic stuff for thousands of years. But here's the problem. As they start to thaw, that carbon decomposes and gets released as CO2 and methane, both powerful greenhouse gases. So, and this is the really crucial part, this could create a dangerous feedback loop. More warming thaws more soil, which releases more gas, which causes, you guessed it, even more warming.
Okay, now watch this. Let's overlay another map. On the right, the red areas show where we grow most of the world's food. See a pattern here? It's pretty incredible. The world's bread baskets in North America, Europe, and Asia line up almost perfectly with those fertile dark green soils called mollisols. Our entire global food system is literally rooted in these specific soil patterns.
All right, let's zoom in from the globe to the scale of a watershed, something spanning maybe hundreds of kilometers. At this level, the main artists shaping the soil are wind and water. So this map shows the sand content across Oklahoma. See those dark brown bands? They're not random at all. They were literally created by the wind, which picked up sand and dropped it along the north side of the big rivers. And this isn't just some cool geological trivia. These sandy bands determine where the region's groundwater is stored, which directly shapes everything from farming to where cities get their water.
Let's keep zooming in, this time all the way down to a single hillside. At this scale, everything is about gravity, how water drains, and erosion.
This image shows a really cool concept called a catena, which is just a fancy word for a chain of related soils going down a slope. Even though they all started from the same raw material, they end up being dramatically different depending on where they are on the hill. Just think about it. Water runs off the top and it collects at the bottom, right? That creates totally different environments for soil to form in.
So let's compare the top to the bottom. Up at the summit, you've got clarion soil. It's well drained, which means the iron in it can oxidize. It literally rusts, giving it that reddish-brown color. But then you go down to the foot slope and you get Glencoe soil. It's a completely different world. It's waterlogged, it's dark and gray, and it has this super thick layer of organic matter because the lack of oxygen slows everything down. Same hill, two totally different soils.
And this has huge, real-world consequences. If you want to farm land like this, you have to install these extensive, really expensive underground drainage systems, often called tiling, just to get the water out of those low spots so that crops can actually survive. Farmers are actively fighting against these natural patterns every single year.
Okay, so far we've been zooming across the landscape. Now we're going to stop and we're going to dig straight down. We're going vertical to look at what's called a soil profile.
A soil profile is basically a history book written in layers of earth. And just look at the story this Tatanka soil is telling us. That thick, dark layer at the top, that's rich with years and years of accumulated plants and roots. But then below that, whoa, that stark white layer? That's where water has leached or washed away all the minerals and clays. And where did all that stuff go? Yep, it piled up in the darker layer right below it. Every single band tells a piece of this soil's life story.
All right, for our final zoom, we're going microscopic. We're going all the way down to the very building blocks that give soil its shape and its function. And these building blocks are called soil aggregates.
They're just little clumps of sand, silt, and clay that are all held together, mostly by organic matter. And the way these little clumps are arranged is called soil structure, and it is absolutely critical for letting air, water, and roots move through the soil.
Now these two charts, wow, they tell a really powerful story. On the left, that's a forest soil. See how it's dominated by those big, stable aggregates? Now look to the right. This is what that same soil looks like after 100 years of farming. All those big, beautiful aggregates have been shattered into much smaller, less stable pieces. And that's not just a physical change, it's directly tied to losing that vital organic carbon that holds it all together.
And if you want to see what stability really means, check this out. It's a super simple but powerful demonstration. When you put it in water, the stable aggregate on the left, the one that's rich in organic matter, it just holds its shape. But the one on the right, poof, it pretty much explodes. This is exactly why soils with poor structure are so easily washed away by rain.
So why does all this matter for growing our food? Well, the science gets incredibly specific here. It turns out that for a corn seedling to sprout properly, the ideal soil crumb size is between 1 and about 7 millimeters. If it's too fine, it's like dust. If it's too clumpy, it's like rock. Either way, that little seedling is going to have a really bad time.
Okay, so if you break those little aggregates down even further, you finally get to the most fundamental recipe of the soil, its texture. And this is simply the mix of sand, silt, and clay particles. It's one of the most permanent and important things about any soil.
And believe it or not, you can actually figure this out without a fancy lab. By taking a bit of soil, adding a little water, and just feeling it, you can get a pretty good estimate of the texture. The real key is trying to form a ribbon with it. If you can make a long, strong ribbon, that means you've got a lot of clay. If it won't even form a ball, well, you've got mostly sand. It's an amazing skill you can learn, to literally read the soil with your own hands.
So, we've been on a pretty incredible journey, haven't we? We went from global patterns that are shaped by climate, down to a watershed carved by a river, then to a single hillside telling a story of drainage, and finally, all the way down to the microscopic building blocks that decide if a single seed will even sprout.
The world under our feet. It's so much more than just dirt. It's this dynamic, structured, beautiful system that connects our climate, our food, and our water. So the next time you step outside, just take a second. What story is the soil right beneath you trying to tell?